Today I want us to talk about a topic I dread and fear so much, and that is when property catches on fire. Whether it's a car, a building, anything. When it burns down, you lose all your investment, blood, sweat, and tears. This is one of the campers I've been working on for a while, and today I almost had a scare of my life. I tell you what happened. I asked the guy to wash this car. And now I found a fuse that cost 20 cents. Almost bent down the car. Now, this coin, I guess maybe when it was cleaning, a coin falls in here, shorts the circuit. What's supposed to happen, the fuse box is supposed to cut the fuse, which is this one. This is the 10 amp fuse that could cost me 10 cents, but look at what was done to it. Look at what was done to it. Right? Look at that. So I put the key in the ignition and I see smoke here. I immediately cut off the ignition, checked, I found a coin, pulled it out, but I was worried, why would a fuse not snap? And this is what I found. Of course, I've replaced it with a good one, but this begs us to discuss. This episode is dedicated to all these DIY guys who are building campers and working around electricity in a camper or an RV, okay? Now, I've seen quite a few videos online of people losing their campers to a fire. Now, that doesn't mean they are DIY guys, and they could have taken the camper to a person who did an inadequate job, did not follow the right standards, and all they had to do is pay a person to get it done, and then the person may not have followed certain procedures, and that leads to a fire. But nonetheless, electricity is not the only thing that can start a fire. You could have a gas leak in a camper, you could have a lightning strike, or many other possibilities. You had a candle running, and whatever the case is, fire is not ultimately started by what I'm about to talk about now. And to those that have experienced such an ordeal, I can only imagine. I mean, I've put my blood, sweat, and tears in the camper. If I lost it to a fire, I'd be devastated. Now, adhering to what I'm about to share now does not mean you are fireproof. There are still many other elements than safety precautions you need to have. You could be cooking and something happens, you could be smoking, and whatever the case may be. And to those that have lost their campers and RVs to a fire, I can only pray that the experience does not rob and take away from you the desire to explore the world, the desire to share your memories, to go, travel, camp. Your camp life experience may not be shattered by the experience. It is such a painful experience to lose property to fire, but if it happens, you know what? May you soldier on, get up again, go back, camp, get another RV, restart, rebuild. Difficult process in life, but you have my respect. All right. What I want to share with you is a 12-volt system, right? I consider this to be the most deadliest and dangerous setup in all the other systems. I am running a 12-volt system, so don't get me wrong in what I'm saying. I am running what I define as the most dangerous. Now remember, there could be a 24 volts, 36 volts, 48 volts, 96 volts, and other systems. Am I within frame? Yep, I am. And many other systems. Why I consider this the most deadliest, I'll explain and break that down to you. But what's important is that even though 24 volts is easy to manage, easy to run through, it is by far the most dangerous in a setup of a fire hazard. It is the killer. If anything bends down, in most cases, if you don't follow the right steps, 12 volts is far more dangerous. This does not mean 24, 36, 48, or 96 does not have the same replicating effects. If you don't follow standards in any of the systems, you'd still lose your systems to a fire. Now remember this, in the world of electrical engineering, voltage can also cause a fire. Resistance can start a fire. I mean, if you've got a system, let's say you've got voltage there, your current flowing through a certain resistance and back. Now, you've got current flowing in a system, you've got resistance, and then you've got voltage. Any of these three elements can start a fire. In the world of electronics and electrical engineering, any of these elements are deadly if not properly respected. But in my assumption, this is by far the most deadliest. For instance, 100 volts, 100 amps, and 100 ohms. I worry more about what 100 amps can do versus the other two. That does not mean the other two are not deadly. That does not mean the other two are not a threat. But I would rather risk you get where I'm going with this. Current in a system is far more devastating. Now, there is the golden rule in electricity. They say current burns and electricity shocks. So don't get it twisted. What burns things down, it's usually current. All right? Now, why do I say, how am I associating current to a 12 volt system? Is there no current in a 24 or 36? There is. But why is a 12 volts why is a 12 volt such a threat in my analysis? Let's break that down. Guys. All right. Now, let's say I've got a resistance. Remember, resistance could be a stove, an iron, a kettle, whatever takes power, right? Voltage pushes. It's a potential, the power to push electrons through a system. What flows in the system is not voltage, it's current, right? The person would say, there was a 300 volts passed through a system. The voltage never moves. It is current that moves in a form of current, right? I don't know what I just said, but you got me. So current is what flows in a system. Current, like a river, like water, it flows. That's the current. Now, the power of that current is ultimately everything. Now, let me give you a good perspective. 1 amp can run a camera, a light, let's say CCTV. All right? Sorry about that. 1 amp can drive CCTV systems. 300 amps can power a submarine motor, right? Like literally a submarine motor. Volcanic lightnings, I think they go between, volcanic lightnings range between 5,000 to 1,000 amps. But I want you to pay the significant understanding of why these two numbers are no joke, right? That's why I was worried about 100 amps in the earlier demonstration. But now let's take this further. I've got a resistance or a stove, right? My stove is labeled 230 volts and 3,000 watts. All right? Now remember, power is comprised of voltage by current, right? The A. This is what power, this is what the 3,000 is for. So whenever you see 3,000 watts and voltage, what's missing in between there is the current to make up that number. For instance, I've got a 12 volt system. I've got a 230 volt system. I'll just choose these two examples for now, right? Now, in this system, let's rather put 2 dots there. Now, we know that we are looking for 3,000 watts. Same thing here, 3,000 watts. How do we use 230 volts to generate 3,000 watts? That's the stove. That's what we have. That's the kind of power we need, right? It means we are going to say 12 volts multiplied by a certain number of current. So 12 volts is the voltage. By this current, it will give us power. So let's just do this on a neater page so I don't confuse you. All right, 230 volts by such and such current must give us 3000 watts. 12 volts by a certain amount of current, amps, must give us 3000 watts. Let's also do a 24 volts and 48, just for argument's sake, or to give you a better perspective. Now, what current are we looking for in these three systems? I hope I'm still within frame. What current are we talking here? Now, to achieve 3000 watts in a 230 volt system, we need close to 13 amps, right? So it's 230 voltage by current gives you power. Now, in a 12 volt system, we need 250 amps. You see where the danger is. Now, in a 24 volt system, like this is 125 amps, and then this is 62 amps, right? Now, look at this. Let's bring the 230 here so you have a better perspective. In fact, let me put a huge system, three-phase, 400 volts, by a certain current, 3000 watts. How much current do we need to run that system? 7.5 amps. Now, what are you realizing here? The higher the voltage, the lower the current, the lower the dangerous one. Now, remember, we have got voltage, we have got resistance, we have got current, we have got power, right? Voltage, this is V, this is R, this is I, this is watts, right? Whatever. My point is, of these four brothers, this is the dangerous one. This is what bends things down. So in a 400 volt system, we only need 7 amps of the dangerous stuff to get 3000. But on the 12 volt system, we need so much of the dangerous stuff to achieve the same answer. So the lower the voltage, the higher the current to achieve a certain power. And this current is what makes the system more dangerous. I don't know if you're following where I am. So current for me is the killer, regardless. Even though voltage would shock you, electrocute you, and stuff like that. So what are the issues? What causes that devastation in a 12 volt system? It is always two things: wiring and connections. This means loose connections. These two, 1 and 2, the type of wire you use to allow more current to travel in the system, and the kind of connections you use, whether it's a bolt, a nut, a lug, whatever you're using. How are you crimping the lines? How are you ensuring that there's a stable, more robust connection? These two things will always protect your systems. So I want us to go through what I've done in my system, how I've upgraded wiring, because remember, we are dealing with a 12 volt system. Once you hear this term 12 volt system, think of these two concepts, because we are talking high current. And high current means anything can bend down at any moment, right? Remember, you have current, you have power, you have voltage, and resistance. Of these three, this is by far the most dangerous one. So current can slowly cook wires and connections. Voltage, on the other hand, can cause an explosion, can cause a arcing, can cause, but this can bend down your stuff. All right, I hope you're following through my train of thought. You're following what I'm trying to get to, but I want you to focus on these two by far. Why are we using specific cables? Just because it's running doesn't make it safe. Just because it switches on doesn't make it safe. How much current are you pushing in that system? How much current? I was charging my battery earlier today. It was at 175 amps. And a part of me is like, that's welding electricity right there. When you are welding, we're talking 121. Just that arch, when you put a welding rod or arc welding or TIG welding, whatever type of welding systems, industrial welding systems use 300 amps and so on. And that's what you are running in a camper. And if you don't safely adhere to the rules that protect that system, give it more airflow, more flow, more bandwidth, more cable to allow these currents to flow, the electrons to flow. You cannot you cannot switch on a 12 volt 12 volt system and turn on a 3000 watt stove and expect not to see heat in any way. That heat has to be managed. How do you do that? You work around the wiring. Okay, let's go to the camper and go through every single step, from the solar panels to the batteries. I've got 400 amp hours. That's 400 amps ready, but it must be contained. It must be contained and regulated to ensure that it doesn't start a fire. Okay, let's go. All right, hi, thank you for sticking throughout the video. And now that you're in this part of the video, let's go through it. First and foremost, the most important part of the nose cone, it's temperature. Remember, there can't be fire without heat. So I've got about 8 sensors, and I'll take you through each and every one of them. I've got a sensor on the positive terminal of the battery. This is a 400 amp hour, and I always thought this is reflecting, but it's just my spare fuses. Let's just move it to the side to kill that reflection. I've got a temperature sensor to monitor the terminal. There's a mega fuse under that, but just to monitor the temperature there, that goes into the Sebo, so I can monitor it from the app or the VRM portal. I've got a temperature sensor on the aux of the shunt. There we go. I've got a temperature sensor on the aux input of the shunt to monitor the minus terminal. I have got a temperature sensor that monitors the environment of the nose cone. This is connected to the temperature controller. There we go. It's on 20. Let me find a lighter and demonstrate how it works. It's on 29.2 now. I'm just gonna heat it up for a few seconds. Watch. It climbs up at 39. There we go. And it goes on. Alright. And then it drops to 37. If it drops to 37, it goes off. And it should go off there. But you can program it to what temperature would work for you. I've got a temperature sensor just behind the MPPT. I've got a temperature controller, the one that's built into the multiplus, and that's to also run the fan. And all these inputs are 4 inputs are going into the Sebo, and 2 are going into the temperature controller. Why that is important, it's so that you just monitor the culprits. Anytime a fire would start, it will always most likely be the main battery, because it's got a lot of current on it, right? So check the terminals. Is it heating up? Check the cells through the BMS. There's also a temperature controller on the DALI BMS, and that's to monitor. As soon as the temperature hits a certain number, I can quickly attend to it than to wait for things or disaster to fall, right? Now, let's go through the wiring. Now, I've got, look at these 2 cables. These are 225s. I wanted to run this earlier, but I changed my mind. Is there a way I could focus on this? Come on, there we go. So I've put a lug, hex crimped them, and then put them back to back on 225 lines, so this becomes one single 50. You get what I'm saying? So it's come on, it's 225s. There we go. It's 225s that are both connected back to back to create one big cable. It's because I couldn't find a 50 in the shops. So I've got 235s that make up 170. Terminals, lugs back to back. That's the main output from the positive line of the battery to the isolator. From there, another fuse out, 2 235s to the main positive bus bar. The same thing on the negative bus bar. There's 235s bond together, and then I've made through a thick copper tube, flattened it up and created a bar for the negative terminal. And then that goes into the shunt, and then from there, sorry about the view, from there, from the positive bus bar that's delivering at 70 millimeters, the same thing on the negative. Then I've got individual, this is a 35 positive, 35 negative. This goes into the multiplus. I would have loved to run a 50, but considering that the distance is like less than 400 millimeters, I was comfortable with that. I've got two 35s going to the MPPT, and then I've got a 126 from the main alternator going all the way to the back of the car. And then I've got a 16. I downgraded to a 16 to allow for the input and the output on the main Orion, right? The recommendation, of course, is a 25, but I felt from here to there, it's a very short distance, so I ran a 16. It's a very short run. But on the long run in the car, I did put up a 25. Thereafter, there is one 25 that feeds into the fuse box, and then every other thing goes through a fuse, of course, goes to their respective appliances, right? So what's mostly key and important, something you never compromise of, remember that a 12-volt system like this will always exploit weak connections and thin wires. If there's a thinner wire somewhere, it will exploit that and create heat, and from that heat a fire would start. So whenever, let me give you a scenario before I close this off. Whenever you hear the word 400 volts, think heavy insulation. Think don't touch it. It will stop your heart instantly and electrocute you to death. 400 volts would electrocute you. But when you hear the word 400 amps, think heat, think burning, because fire always comes from heat. And the culprit for heat in an electric system is current. And what makes a 12-volt system susceptible to current, it is because it is the one tool it uses to manipulate power output. I hope I was clear on everything. Remember to keep your systems grounded, run your earth lines, just protect your system. And the intelligent part is that I did introduce a Sebo to monitor the temperature from wherever I am. Just go through the app, you get to see what's happening in the nose cone. And all this manageable, simple, all concealed in a nose cone. One of my favorite things is that every now and then I'm draining a lot of power from the multiplus. Say maybe I'm running a toaster or anything, the fan kicks in automatically. It always reminds me that, hey, there's 1, 2, 3 happening in the camper. Oh, by the way, I custom made this sticker, but it will be part of the episodes and branding that takes you through all this. But what's important here, Victron systems, Narada batteries, Dali BMS, and JA solar panel. That's what's responsible for the power system in the camper. The rest, just as normal as always. Thank you so much for watching. Truly appreciate your time. I hope this was informative. Till the next one, I'm out.